We're going to lift the hood of some real implementations of cache coherence and go down to one more level of detail exactly how this can be implemented in real hardware. This example is what cache coherence protocol found in a system called Enterprise Server 6000 at Sun, and it's very similar to like the P6 cache coherence protocol that Intel implemented as well. We're going to look at a specific implementation of cache coherence, which is called dual tag cache coherence. And here we have our normal cache, the way we remember it, with an address tag, state, and data organized in a cache line. So this, even though I'm showing a direct mapped cache here, this may of course be some kind of associative cache. And this tag here, this cache is where the CPU is going to do its lookups. And the state that's stored here is going to be the permission state, telling exactly what kind of access right the CPU has at exactly this point in time. We also have replicated the state for each cache line stored in this state cache down here. And here, so here we also need an address tag, and we also need the same number of state bits here. And this is information that the bus snoop will look into when it snoops on bus transactions. So this avoids that the bus snoop will always have to look in the same cache as the access has been done by the CPU and slow down the CPU. So it has its own little cache that only has state information. We call these the snoop tags, or this is the obligation state. It tells what obligations we have toward other cache coherent transactions in the system. So the cache access state machine can still put bus transaction in some queue, and this queue will arbitrate for the bus and can broadcast those transactions on that bus, and the bus snoop here will still look at all those broadcast transactions from itself and from others. We're going to look at the same example once more. We're going to look at the how to handle coherent writes in the cache coherence protocol, where the middle thread wants to perform a store operation to cache line for which it doesn't have store permission. And as we remember, the cache coherence protocol will implement this kind of invalidation. So here we have the two of those three caches that we saw in the previous example. We have the middle cache that performs the store. That's the CPU that sits here, and it's going to look into this cache access protocol. And then we have, in blue, we have the snoop state machine that may be of the right or the left cache or CPU of that picture, because they would perform exactly the same operation. So it's going to see what happens now when we do this upgrade miss in our state machine. So first of all, this is the initial state before the write occurs. We have a shared cache line in the middle cache, and the right cache and the left cache represented by what's going on in the blue box here. And the CPU wants to perform a store operation, which means we will do a lookup using the cache access state machine here. Says, whoops, it's in state shared, this cache line. I can't really write this right away. I have to tell the world about this. So a bus invalidate will be sent out on this Snoopy-based bus. And this bus invalidate will be snooped by the own state machine as well as the foreign bus snoop state machines. So the own state machine here will see, aha, here is my bus invalidate, and it will put a special sort of acknowledge token in an in queue here. So the bus snoop can store transactions, put pills in an in queue here, and this is a blue pill, which is acknowledged saying, I just saw my own bus invalidate. And the left and the right systems will instead, their snoop lookup will say, I have to put an invalidate pill in my in queue. What also happened here is that the snoop states changed during that lookup. So the snoop state changed from shared to modified for the middle, and for the right and the left, it changed from shared to invalid. So these are the snoop obligations that happen here. What we have, how the rest of the world looks at us. The rest of the world is going to say, the owner of this cache line from now on is the middle, because it has the cache line in state modified. However, there may be other pills as well in these enqueues. It could take a little while before the respective implementation, cache coherence implementation, can eat all those pills, because the lookups from the CPU are more important than the lookups from the cache coherence itself. So, for example, in system to the right here, there could be a couple of pills from earlier transactions that we still haven't chewed up, and in the middle system, there may be no pill, so we could eat this pill right away, saying, acknowledge, I hereby see that my invalidation has made it up to the bus. I can declare success. I can change the state in the cache to modified as well. And since it's now changed to modified, I can allow that cache line to change its value. Still, the invalidation has not been performed on the cache to the right here, because there are other pills sitting in the way. So here we have a system where the middle cache has changed the value for this specific cache line, and there are other replicated copies of the same cache line that still maintains the old copy, the value of that cache line. And the CPU in this blue system here may actually read this old copy, even though the CPU in the middle system has already modified its copy. Eventually, those pills from earlier transactions will be consumed, and eventually the invalidation will take place in the right system as well. So when the blue pill is eaten here, then this will change to state invalid as well. But that may happen at a later point in time. So now we saw how this write transaction was performed in this dual tag system. Now we're going to see how this read transaction is performed. So it's a cache coherent cache to cache transfer once more that we need. So we need this to happen, that the data from the middle cache has to be sent to the left cache. Looking at what's going to happen in our state transition table, now looking at state transition that the left cache will do, starting off in state invalid. It sees a CPU read request. It sends out the bus read to share request. That's what it will do. Load invalid implies bus read to share request and change the state to shared. And the other caches will see that bus read to share request. More specifically, the cache line in the middle that now is, before this happened, was in state modified, will see this bus read to share request and change its state from modified to owned. And that is also reflected in the state diagram below. If you're in modified, see bus read to share, you go to owned, and you provide the data. So we have to provide the data back as well to the requesting processor. Okay, so this is what happens in the dual tag system. This is the initial state of affairs. Now the middle CPU is the one here, the one with the cache line in state modified. Its duplicated tag is also state modified. The left cache starts off with invalid in its data cache, and invalid also in its snoop tags. Tries to perform a load operation, sees state invalid, and the state diagram here that defines that we need to send out the bus read to share request. The bus read to share request is snooped upon by itself and by the other snoop systems on the same bus. So now means we will see our own read to share request, and we'll see a bus read to share request that's queued up in the middle cache. So it may still take a while before the middle system eats up this pill, and eventually, while we're waiting now for the middle system to eat up the pill, in this situation, it's actually the left cache is not allowed to eat this pill. Okay, because before you eat that pill and you can change the state down here, you also need the data. You need to fill in this data here with the cache to cache transfer before you can change the state. It's quite natural. So it's going to sit there at the head of this queue, and it's going to block any other pills that landed in that queue after it. until the data is returned. And when the data is returned, first at that point in time can you change the state to shared, but now this cache line contains the new and exciting value of the cache line. And this also explains why we actually can implement coherence even though the invariant didn't hold that there could only be one value. There could be several values, several copies, and also several values of a specific piece of data. This is the mechanism that actually makes sure that we still can keep coherence. For as long as nobody talks to a cache, for as long as that cache sits by itself, not eating any pills, and just keeps working locally in this cache, it's okay that its value may be sort of out of sync with the rest of the world, because the only way it can communicate with the rest of the world is by eating these pills. And when it starts eating these pills, that means that it's sort of going to catch up time-wise with the rest of the world. So there is some kind of logic time here. And when people reason about this kind of system, they often use a concept called Lamport clocks, reasoning about what's really happening in a system. So even though from a wall clock standpoint, the values stored in caches for the same cache line may be different, that's if you look at logic time or Lamport time, then actually there cannot be several copies. It's only in wall clock time and not in the logic time. So this has a side effect that even though there can be several different values of the same cache line, it's impossible to write a program that would be able to detect that. Okay, and since you can't write a program that can detect it, it's okay to have the sloppy definition, even though we know, studied this cache implementation at the very detailed level, that there may still be, just looking at wall clock time, several different values in the system. So if there isn't any more read to share requests heading for the middle cache, well, it's already in state owned, so we don't need to change state, and we also need to reply data to those requests. I'm not going to show that down at the dual tag level. So in summary, dual tag is an implementation technique that enables bus snoops to happen at the same time as CPU lookup. So you can actually have a quite heavily contended snoop bus, and you can still allow CPUs to make quite a lot of progress while you're handling all those snoops. We noticed that the data may actually have several values at the same wall clock time, but in logic time, it can't. So software cannot, you cannot write a program that can detect the fact that there is, the system may look incoherent. If you took a picture of it in wall clock time, and you could take a picture of the different states. And we can probably convince ourselves, looking at this reasoning about logic time, that also the value change order is indeed maintained in this system.